Hello, my name is Kane Wilson, and this is my capstone project. In this project, I will be building a Geiger Muller counter, which is a radiation detection device. So, my guiding question is how can I safely and efficiently plan, research, and manufacture a Geiger Muller counter? So, some safety I'd want to go over because we're working with high voltage and radioactive substances is besides from having common sense for high voltage, using the one hand rule is an easy way to reduce risk. The rule is to always have one hand behind your back. This stops you from accidentally running electricity through your heart, which is not good for you. For radioactive substances, minimizing contact reduces most of the danger, since your body can handle a bit of radiation if it's a quote unquote safe source. And by safe source, I'm talking about like a very small amount of alpha emitter material. This type of radiation doesn't penetrate the skin, so there's little to no risk. And the total emission of the source is similar to what a person living in Squamish would experience by just being near a large amount of granite, because granite does release a small amount of radon gas, which is radioactive. Here's just an overview. So, what is my project? A bit of background. It's a Geiger Muller counter. It uses a sensor that is super sensitive to radioactive particles, and it detects radiation, and that's a really distinctive click sound. You might have heard it in some TV shows or movies. So it sounds something like that. And it was first invented in 1908 and then later put into production in 1928. During the Cold War, Geiger counters were used extensively in America and Russia and were sometimes distributed to citizens in case of a nuclear event. So why did I choose to do this project? I chose this as I was working on this already as a hobby before the capstone project started, and I had already put a lot of time into researching this. I also saw this as an opportunity to develop my engineering skills in case I get into engineering school. And I also just like building and working with my hands since I was little. So doing this helped me continue to develop a bunch of skills like soldering, welding, and assembling circuits. So here's some field-specific skills that I learned, like focused towards electrical engineering. So I learned how to read technical documentation. So this is essential to understanding the parts that you're using and the functions and tolerances of those parts. These are of the NE555 chip, which I based my audio system for my Geiger counter off of. Here's SPICE simulation software. It's a type of program to build, test, and simulate circuits. It's often used by electrical engineer students before building the physical circuit. Developing or prototyping circuits on LT SPICE cuts down on development costs and lets you make worries or mistakes without too much worry. Prototyping, this is a prototype of the Geiger counter. So prototyping before creating like the permanent PCBs or printed circuit boards allows you to test your simulated circuits in the real world because the parts will act slightly differently with things like heat or pressure. And so it's cheaper to mess up on a prototype than it is to do on like a full-fledged printed circuit board. And here's some circuit testing. So this is an oscilloscope, and this helps you analyze your mistakes after prototyping. This oscilloscope just represents voltage versus time on a graph, and it's really helpful for troubleshooting weird signals, noise, or interference. This is from a PC design software, and it allows you to create printed circuit boards where you can easily mount all your components and finalize a product. It also has a lot of nice tools for routing traces, plotting components, and preventing noise. Like this large blue part is a ground plane, which reduces a lot of the electrical noise. Soldering is essential to know, as it actually lets you put together the circuits. So developing the skill early makes things easier in the long run. Here is a software called GitHub, and it lets you store a lot of project files and stuff, and it lets other people contribute to projects and things. It makes it just the workflow much easier for developing like a bunch of stuff. This is pretty standard for a lot of engineering. So learning to use the CLI and storing my project file sources and documents there was good practice with their CLI. Use the physical project section. So this is not the project, but I'm just showing this as an example, is that this is pretty complicated and overwhelming to look at. So starting something like this is much easier to break up. So here I have a high voltage DC power source. And this powers the Geiger Muller tube, which is the trigger mechanism for the audio system. And then I just designed each block from most simple to most complicated. So here's the trigger mechanism. This is using the NE555 chip I mentioned earlier. It wasn't too bad. It was pretty quick, maybe 3 or 4 hours. This is the audio system. This was also pretty quick, about the same as the other one, like 3 or 4 hours. And this one was much more complicated. This was plus all the theory and research I had to do, like 40, 50 hours figuring this out. But now I have the knowledge to do it pretty quickly. Could probably get it done in an hour. And this was also done on the previously mentioned SPICE simulation software. Here is the finalized schematic of it all on KiCad, which is like a suite of different circuit softwares. So this one's for creating schematics, and this one's for PCB. This is the finalized PCB ready for manufacture. And then also on KiCad, this is a 3D model of the same board with all the pick-in-place components on it. So I could send this off to a factory, and it would be done. But it was quite expensive to do that, so I ended up just buying the circuit board and the components separately, and then just assembling it. Unfortunately, the Trump tariffs really messed up the manufacture and shipping, so I was unable to get the PCB in time. I ordered it around 2 months in advance, but yeah, nothing I can really do here. So these are some of the challenges I had to go through. So learning all the SI units and lingo for electronics felt like a bit undertaking, but it got easier as I was exposed to it more from data sheets and lectures. Here are logic gate symbols. These were confusing too, but in the same way as the SI units, as I was more exposed to them, it got a lot easier. Here is the SPICE program called LT SPICE. It was rough to learn because it has a very old and confusing UI, but it was by far the most helpful program for me. It helped me prototype and test a lot of circuits very quickly. This number circuit math was very difficult. It was too difficult for me, too complicated, so I had to work with my mentor to figure this one out. This area is definitely a place where there's much more for me to learn. I think knowing university calculus would have been very helpful for this. And then just all the theory. I knew most of the basic theory, but a lot of like the DC to DC converters and flyback, or like the flyback in this project, were quite difficult. The transformer and inductor theory was also tough, especially with all the confusing like hysteresis curves, core saturation, and learning about like magnetic shunts. Here's the sources. I compiled it on the GitHub, which I mentioned earlier. There was too many to fit here. There's probably 100, 150 sources. And So here we'll be going into some of the footage I compiled from all the research and testing. Okay, so this is around 50 hours of footage compiled into about 7 minutes of the capstone project. Here I am installing and learning how to use LT-Spice and KiCad, which are two pieces of software that I'll end up using a lot in this project. So pausing here is me learning how to create the IC chip symbol on KiCad. Here is a custom symbol I made for a piezoelectric speaker. This is the finished audio system with the transistor oscillator. So this is the beginning of me learning how to use LT-Spice. So you can see there's a signal at the top and then the circuit on the bottom, and they are both simulated to close to real-world accuracy. Pictured on the top is a circuit of for testing capacitor discharge time, and on the bottom you can see a wave, and that just shows how long it's taking for the capacitor to discharge and how quickly it's charging up. Here's a data sheet for a 555 timer, and I used this for the one-shot generation circuit. And here's the full one-shot generation circuit used to trigger the audio circuit. This is an old schematic for a DC flyback converter for high voltage. I ended up not using this one, but it was helpful for planning out some stuff. Here I started working on a flyback driver, but I ended up not using this chip and improved on it later. Here is a example circuit from a data sheet, and I ended up using this to help design me the flyback converter. And this is on analog.com. It's very helpful for IC chip component design. I ended up using this quite a bit, especially with all the data sheets and lectures they had. Here's a really good diagram I found on DC to DC converter topology. It helped simplify things a lot for me. So in the top right is my flyback design, and as you can see, the signal is quite wavy, which is not good. So as this goes on, it's gonna be fixed. Around here, I start looking for radiation sources. So I'm looking for closed uranium mines nearby to see if I can grab some raw ore. But I couldn't find any, so I ended up using a americium 241 source from a vintage fire alarm. So freezing here, I've gone back to some basic transformer theory uh, so that I can see what's messing up my signal on my flyback converter. Here I'm comparing the signals from my transformer testing and my flyback testing to make sure there's no bugs or any stray frequencies. And I'm starting to get voltage closer to what I want around here. Here is some research that I did using the inductor and transformer design handbook. This was really helpful. It cleared up a lot of things for me. Ended up kind of saving the project a bit. Here is a screenshot from a software called Circuit.js1. It's really helpful for visualizing the flow of current. Here I'm just referencing the data sheet and I'm looking at the signal, and it's starting to get a little bit better. There's this like Indian dude and Dutch guy that does really good electronics YouTube videos. I can't remember what name they had, but it's very good. The chemistry tutor was also very good for this. You'll see him pop up every once in a while. So I ended up using a lot of slides from this linear circuits course from UBC. It covered a lot of like the basic stuff, so it helped build a little bit of fundamentals. Here I'm finally getting the right switching mode frequencies, which is nice. Off camera, I designed a forward switching DC converter to create the supply voltage for the flyback converter. This probably took 10 hours plus maybe 30 for the flyback, which was mostly just research and learning all the theory and tested. And it's all just been connected up here. Now I'm just finishing up the schematic and putting everything together as like a nice big poster. Here's the finished schematic. It's mostly done. There's like a couple polishing things I end up doing, but nothing major. Here's the beginning of the PCB design. So I've just grabbed all the components and put it into this separate software. And here is the first design. Decide not to order it and redesign it. Polished up design and routed all the traces here, and so here I'm on to ordering it. Going through part picker and part placement files. I'm generating all the drilling and cutting patterns now, and this is the final design, and this is the order screen. This is just some footage from me building the prototype. This is that was at a lab. This is in my house. I'm just checking to make sure all the Wires are soldered correctly. I'm just documenting to make sure it's easier next time. Just more documentation. There is the main trigger and audio section. The thing in the aluminum kind of cage looking thing, that's the high voltage flyback transformer. Okay, I wish I could explain what the hell this is. Where's my damn radiation at? Am I stupid? Okay, just drop that. Okay. Yeah. But what? Why did I break it? Oh! It only happens when the radiation is pointed at it, though. I don't know what kind of light that is. I'm kind of scared. Okay. Man, that's not supposed to happen at all. Thought it was pretty funny. I did fix it, and I ended up getting a new tube. But here's a picture of the old one glowing like a light bulb, which is not what you want. So with the new Geiger tube, I got some cool like Soviet documents from the Cold War. This is the tube, and the box should be coming up. These are all from the Cold War, I'm pretty sure. They're all like old Soviet military surplus. Unfortunately, the PCB got delayed by 2 months. They were supposed to come in like a couple days, but the Trump tariffs like messed it up midway through shipping, so it hasn't come still, unfortunately. Otherwise, I would have something to show, but I have the rest of it, or I have all the theory and stuff for it, so it's, yeah, just kind of sucks. But thank you for watching, and hopefully by June I will have the finished circuit. Okay, thank you, bye bye.